Previously, we came up with a precise definition for the net area of these regions that are bounded by curves and the x-axis. And we also looked at ways that we can we introduced the notation of a definite integral. And what we're going to look at today is how geometry can be helpful in evaluating certain definite integrals, right? And so we're just going to go through a few examples to illustrate that with any definite integral that you write down, you can draw a picture that illustrates what that definite integral means. And then depending on the type of shape in that picture, we might have some formulas from geometry that are useful. So let me start out with something that looks like this, right? So we have the definite integral, the lower limit of -3, upper limit of 4, and our function is just a constant, right? So in terms of the the notation that we came up with, our f of x in this case, the integrand is just the constant function, 5. And then the interval here, your x would go from -3 to 4. So this would be the interval. So basically, if we can sketch this function over this interval, it will give us an idea. Can we find a formula from geometry that will enable us to come up with what this number is? All right. Well, constant functions, you may recall, are horizontal lines, right? So first, let me draw the xy plane. And what I'll do is I'll draw the function and so forth in a different color. So the function f of x equals 5 is this function, right? So that's your f of x equals 5. Now let's mark off the interval. So -3 somewhere there. I mean, you can put other marks if you'd like. And then 4 is there. So what is the region here? Well, remember, the region it's bounded between the graph of the function and the x-axis. Now, this function is entirely above the x-axis, so then my region is this region right here. And it's everything in there. So I'm pretty sure you know what that region is in terms of a shape. This is a rectangle. And we know the simple formula for the area of a rectangle. It's our length or width right here, and then times the height. And the height is exactly equal to the function value of 5, right? So we can write down what this is. So therefore, using geometry, right? So basically, we're just using calculus as the means to denote this, right? It's just the notation. But as far as evaluating, because the region is such a simple region, this is where we can go back to geometry and say that it will be our length times width. Now the length, this distance here, just take the larger x minus the smaller x, and you'll get a 7. And then, of course, as I said earlier, this is just the height of the function, so that it's 5. So that so let me write it this way. So it's the area of the rectangle, which in this case is 7 times 5. So that's 35. And if you wanted to say square units, you could do that because you're using area. But what we're saying is this definite integral represents this area, and then geometry tells us that that area is 35. So it's a nice connection between, the calculus notation, the visualization of the region, and then the formula from geometry. So a really nice connection there. All right, so let's just do a few more of these so you get a sense of, what types of geometric shapes are you expected to work with. So here's this one. This one goes from -2 to 4, and then the function is 2x dx, right? So our integrand is 2x, and the interval here is from -2 to 4. So what we have to do, again, is to sketch this function over this interval, come up with an idea of what the region is, and then what formula from geometry will apply. All right, so let's sketch this, see what we have. Y equals 2x is a linear function. The y-intercept is 0, so it passes through the origin, and it has a positive slope of 2. So basically that. So that's y equals 2x. Maybe I should have done it in a different color. We can shade the region in a different color. And then, so let's say this is 4, so roughly half of that going this way will be the -2. And again, remember what the definition of our error problem, that it's the region between the x-axis and the graph of the function. So that means the region starts here, and we have that piece that now happens to be below, and then that piece that happens to be above. All right. So unlike our previous example, part of the region is below, that's this part right here, and then part is above. So how do we break this up? Well, we can see that these are right triangles, right? These are right triangles. And we know the formula. So for a right triangle, we're going to use the formula 1/2 base times height. So let's go ahead and label certain things. This distance here is 2. This distance here is 4. That, measuring it from the origin, the fact that the line passes through the origin makes it easy for us to identify the base of these right triangles. The height for this one, well, how high does it go up? Well, to figure out the height here, we need to know the y value. Since we know the x, we can plug our x into this function, and then we get a y value of 8. So the height here is 8. The height here is actually going to give us a negative height, and that's because it's going down, right? Because if you plug this x value into this function, you're going to get that height is -4, right? Because you'll have 2 times -2. So let's write it down. So it's it's going to be one of those net area calculations. So we have -2 to 4, 2x dx. Well, the area, the net area of the rectangle, the right triangle that's below the x-axis is 1/2 times base times its height of -4, right? So that, keep in mind that this is a net area, right? And then the bigger right triangle in the first quadrant here will have an area of 1/2 plus its base is 4 and its height is 8, right? So, if you wanted to, you could actually factor out the 1/2. 2 times -4, that's -8, plus 4 times 8, that's 32. negative 8 plus 32, that's a positive 24. So we have a 1/2 times 24 for a final answer of 12. And keep in mind, again, that this is the net area, right? And that's the value of this definite integral. All right, let's look at a third example. And this one goes from 1 to 5, and it's negative 2x plus 4 dx. So in this case, the function is negative 2x plus 4. So it's another linear function, but now we know it's not going to pass through the origin. And here the interval x goes from 1 to 5. Let's see if we can sketch this. Now, again, there are lots of different methods that you would have learned as far as sketching the graph of a line. So 1, 2, 3, 4, 5, basically there. And for a line, once you recognize that the function is linear, you only need 2 points. So we could actually just figure out the y value when x is equal to 1. And actually, yeah, so when x is equal to 1, the y value is a positive 2. So let's say this is 2 right there. And then when x is equal to 5, we'll have a negative 10 plus 4, so that's a negative 6. So let's see, 2, 4, 6, roughly there. So negative 6. And then it would correspond to x equals 5. So the point is roughly there. And then connect those 2 points with this straight line, right? So then what does the region look like? Well, again, it's like this little triangular region there, and then another triangular region there, right? So the nice thing is we can use the same formula, but the problem is we don't know right now what this x value is, because we need to know this in order to compute that base and that base. Like, we know the height, right? We already have the height of the little triangle that's above. This height here is 2, right? Because that's the y value that corresponds to x equals 1. And the height here for this one, that's below, that's your negative 6. But what we don't know is the base. So how do we figure this point out? Well, that's the y-intercept. So we'll have to figure out not the y-intercept, the x-intercept. We'll have to figure out where this function is equal to 0. So we can do a little bit of algebra and take our function, set it equal to 0, subtract 4, divide by negative 2, and then we figured out that it's 2. So then I know that this base is 1, 2 minus 1 is 1, and then this base is 5 minus 2 is 3. So then I can use the same formula from our second example. And so for the first, the little triangle that's now above is going to be 1/2. Its area is 1/2 times a base of 1 and a height of 2. And then plus the bigger triangle, which now happens to be below the horizontal, it's 1/2 times a base of 3 and a height of negative 6. So this is 1 minus 9. And then you end up with a net area of negative 8, right? Again, let me indicate that this is a net area. So again, when you're working with these definite integrals, depending on how the region plays out, like how it's defined, how much of it is above or below, is there more area below than above? In that case, you are going to end up with a negative value, right? So it's not that, and again, I want to emphasize, it's not that we're saying, okay, the area is negative. It basically, the negative is telling us that more of it is located below the horizontal axis than above, right? Let's try one more example, right? And this one will, take a little bit of thinking through. All right, and we're trying to evaluate this definite integral. All right, so again, let's write down what the function is. It is the square root of 16 minus x squared, and the interval goes from 0 to 4. All right. So the question is, do we know what the graph of this is? In fact, if you write it like this, let me write it in terms of y. Right, there is the equation. It's easy to recognize linear functions, right? But with the square roots, you have to be careful, and please do not be tempted to try to say that this is 4 minus x. You cannot take the square root of a difference like that, right? Order of operations, lots of reasons why it doesn't work, right? There's no property of square roots that allow you to do that. So we have to think of this function and think, okay, what exactly is this? Well, this equation here is written in an explicit form where you've solved for y. But we can rewrite it and make it an implicit form. And what I'm going to do is I'm going to get rid of the square root by squaring both sides. So I'll have this, right? And then I'm going to put all my variables on the left, and I'm going to leave my constant there. And then I have x squared plus y squared is equal to 16. Now, I'm hopeful that you recognize this equation. This is the equation of a circle that is centered at the origin 0, 0, and with radius, which is the square root of this, so root 16, which is equal to 4, right? Let me, just as a reminder, if you don't remember that fact, this is the standard form of the equation of a circle that is centered. So here the center, so this is a circle, and its center is at the ordered pair h comma k, and then the radius is r. Not r squared, but r. So it's the square root of this hopefully positive number on the right-hand side. So radius r. So because we recognize this, that will give us an idea of how to sketch this. Now, the other tricky thing with the equations of circles is that once you put it in the implicit form, so for instance, the circle essentially has two halves. You have a top half. If you think as y as a function of x, it has a top half and then a bottom half. Because our original function has a positive square root, then my y values are always greater than or equal to 0. So the top half here, that part corresponds to our original function, the y equals square root of 16 minus x squared. If you just, for instance, if you have a graphing utility that allows you to graph something like this, it might give you the full circle so then it might give you the bottom half. And then the bottom half, in fact, let me do that in a different color and then label it in that color so you can see the distinction. That bottom half of the circle is actually, if you think about it, it's just a reflection of the top half. And the way you reflect functions in the across the x-axis is by multiplying by -1. Right? So when you look at a single circle, there are technically two functions there. You have the top half, which is the positive square root, and then the bottom half, which is the negative square root. So, and for our particular case, since it's the positive square root, we can essentially ignore this part, the bottom part. And then let's see if we can shade it as we've done previously. Well, the interval goes from 0 to 4. So what is the significance of the 4? Well, the 4 is actually the radius. So it goes from, here is the center, and then there is the radius 4, right? And then it's everything between the x-axis and the positive square root. So it's all of this, right? In fact, let me be precise here and label my variables, right? So there we go. So this is the region here that is implied by this definite integral notation. So then the question is, what is its area? Well, it's 1/4 of the full circle, right? Because it covers everything in the first quadrant. And we know there are a total of 4 quadrants. Only one of them here is shaded. So let's wrap it up and come up with the value for this definite integral. So the definite integral from 0 to 4 of 16 minus x squared dx. It's 1/4 times the area of the full circle. Well, the area of a circle is pi times the radius squared. So that's 1/4 times pi times 16 for a final answer of 4 pi. Right? So we are evaluating, right? We're figuring out what the net area is, or in this case, we can just refer to it as an area since it's all, the region is entirely above. So we're evaluating all these areas or net areas, but we're only using geometry, right? Later on, we're going to learn, well, what if geometry fails? What if I don't have a nice formula for, like a circle or a rectangle or a triangle or a trapezoid? What if I don't have those formulas? Then that's where we're going to have to rely more heavily on calculus, and geometry will be less and less useful. So you have a lot to look forward to, and I will see you then.